Good morning, and welcome to the first round of the DevSummit technical sessions. My name is Dave Koenen. I am the Interconnect product manager in Arm's infrastructure group. I manage a line of interconnect IP products for servers and networking SoCs. Today, I'll be sharing with you information on different interconnect technologies and development tools that you can use to develop your next SoC design. And oh, by the way, in this format, I know I'm just a talking head in the corner and not very interesting to look at. The interesting stuff is in the presentation and the chat session, so your focus should be there. Well, you and your customer may be trying to determine whether to build or buy an interconnect and probably have some performance, power, area, and cost goals in mind. And the SoC will have to handle some kind of I/O workload, software tasks executing on multiple CPUs, possibly a mix of accelerators and neural network processors. And you'll want an interconnect that can support different memories, CPUs, I/O types, maybe last layer cache, and maybe multi-chip. As you can see, there's a lot of things to consider, most around features and capability, but you should also consider availability of documentation, support, tools, and development tools. I'll pause here for a second to take a look at those, and if you don't see what you're looking for, you can comment in the chat section. Okay, if you're looking to choose an interconnect, you should also look for good references from existing users. Here are 3 ARM partners with references and quotes from some technology publications over the past several months. We have the AWS Graviton 2, the Ampere Ultra, and both have production chips using CMN 600. And the SiPearl HPC SoC has also indicated they'll be using ARM CPUs and a 2D mesh as well. My favorite is Tom's hardware quote: 80 cores, mesh interconnect, and low power. What's not to like? ARM offers a lot of different interconnect product lines, but for this presentation, I'll be focusing on 2 product interconnects, specifically the CMN 700 and the NI 700 that were recently introduced at the Neoverse product update in late September. The CMN 700 is the 3rd generation of coherent mesh network that connects CPUs, accelerators, I/O, and cache and memory. It also supports CCIX and CXL gateways for multi-socket and multi-chip solutions. On the non-coherent side, we still have the NIC 400 and 450 for ACE Lite and AXI 3 and 4, but for future designs, we are advising using the NI 700. Its ad hoc network has a smaller area footprint and improved tooling to support the next generation of AmbiZ AXI issues like -F and G and H features. Well, for both of these, ARM has been working very closely with our EDR partners to provide support for the latest DDR and HBM memory controllers, as well as the PCI Express root complex and endpoints and AmbiZ buses. I'll start with the cache coherent CMN 700 interconnect, which was designed to support ARM's N2 and other Chi-E processors and CXL gateways. But you can also support other older processor cores as well. The CMN 700 was designed as a scalable coherent mesh with distributed system cache and Snoop filters to support V1 and N2 cores performance levels, as well as PCI Express Gen 5 and DDR5 and HBM3 controllers available from our EDA partners. In addition to the increased capacity and bandwidth, we've also added some advanced features like memory busy feedback mechanism to throttle the core's prefetchers when the memory queues get busy. This feedback has been shown to improve by up to 15% per core uplift under heavy load and system load conditions. Another advanced feature is the memory partitioning and monitoring, or MPAM. It provides software managed cache line allocation of the system cache and memory bandwidth allocation on a per VM and per process thread basis. For connectivity off-die, the CM700 also provides the most comprehensive multi-socket and host-to-accelerator memory solution. It supports both CCIX, rich coherency protocol, and CXL's efficient interchip interface. If you're connecting to a CCIX device or similar chip or chiplet, then CCIX is the better choice because of its rich coherency protocol. If, however, you're targeting, say, memory expansion or coherent accelerators, then CXL would be the best choice for a potentially large number of interoperable devices to choose from. The CMN700 supports up to 32 CCIX or CXL gateways per mesh to allow your workload to scale to the necessary cross-chip bandwidth. Some of you may be familiar already with our public information on the CMN600. Relative to that, the CMN700 is just more of everything. It has more core support, going from 64 to 256, a 4x increase. System level cache has been quadrupled from 64 to 512. We've increased the number of nodes and the size of the mesh from an 8x8 to a 12x12. Device per port we've increased. It used to be only 2 devices per cross point. Now on the edges you can support like 4, even 5 for a single device. And the CHI interfaces and AXI and CXL interfaces for CCIX cross-chip. We've widened those from 256-bit to 512-bit. And the number of device ports. Before we only had 16 memory controllers max, and now we support up to 40 regular DIMM type channels or 80 dual channels. CCIX device ports have also increased. So we used to only support 4, now 32. And we've added self-helper features like the CXL acceleration port, that MPAM that I just talked about earlier, and also a memory access protection via memory tagging extensions. And the CBusy, which I talked about the method for feedback. We also added some hotspot rerouting for, say, if there's congestion points in the mesh where you want to get around to avoid the usual routing capabilities. Well, after building many internal CMN-based reference design in-house, we've come up with several general guidelines for component placement. Generally, we advise placing the system cache, and also called home nodes, and CPUs close together around the interconnect, and then place the external memory and I/O out around the edges. We found that this provides the lowest average latency and even traffic load distribution. For small configuration examples on, let's say, the right-hand side, we advise placing the CPU clusters and system cache outside the mesh fabric. That mesh fabric is the small 8 boxes in the middle. The 4 system caches in the green and the 2 CPUs and the dynamic shared unit layer 3 clusters of N1s are on the bookends, top and bottom. This allows for very short inter-cross-point signal channels in between those cross points to minimize the area due to the fabric. For slightly larger arrangements, say 16 to 32 CPUs and 3x5 or 4x4 mesh, the example in the middle shows the system cache and system filter home node placed inside the mesh fabric. And the CPU clusters are then connected on the outside of the periphery. You can also connect the memory and I/O through the gaps between those clusters. And lastly, for very large configurations and higher core count, we advise placing the CPUs and home nodes within the mesh in kind of like a tile configuration to allow for higher core count and easier chip layout. These CPU home node tile templates can then be replicated with parameterized signals per XY location. Memory and I/O should still be symmetric around the configuration and around the mesh to provide good balance and distribution of cache, memory, and quest, and response time to minimize congestion hotspots. Those single mesh configurations I just covered can be expanded with CCIX and CXL gateways to connect to other die on, say, on a multi-chip module, or some other external accelerator or memory expansion module. Both CCIX and CXL protocols provide multi-chip and cache coherent connectivity, but their features and capability are different enough to warrant retaining both. CCIX has a rich set of coherency operations that make it better suited for, say, distributed layer 3 cache and snoop filtering across several identical or heterogeneous devices. Whereas CXL's host-based coherency policies allow one to make a much simpler, say, memory expansion module or an accelerator device. This slide helps to illustrate the differences between those CXL and CCIX coherency models. The primary difference is where the CPU goes to get page tables from the SMU and snoop filtering. To simplify CXL's device architecture, the host is home to the shared memory MMU and maintains cache coherency in snoop filter states. In CCIX, memory home node, cache, and snoop filtering is located nearest the shared memory that it covers. And Arm is a leading member of the CXL consortium, and we've been working with our EDA partners to develop an industry-standard AmbiZ CXS interface that supports both X or CXL. Arm CMN 700 supports both over the same PCI Express lanes. Arm also offers a superset of CCIX cache transaction that works over the common CXS layer to take advantage of the low latency offered by CXL's data link layer. So from one cross point, one can connect to, say, an RNI for PCI Express, the legacy CCIX gateway, or a CXL gateway, and they share the same PCI Express lanes. And now this same cluster of activity can be replicated with address hashing and mesh support and aggregation for load balancing across multiple gateways. Although neither protocol defines a chiplet PHY, Arm continues to collaborate with our EDA partners to allow CCIX to work over the customer's preferred chiplet PHY like XSR or a bunch of wires or HMI or others. To complement the CMN 700 coherent network, we also introduced a new non-coherent network on a chip interface, the NI 700. It is a revolutionary change from our current NIC 400, both in features and in tooling. The NI 700 is a complete composable non-coherent NoC that packetizes AXI 4 and 5, ASLIDE and APB and other protocols over a generic transport links. It takes up less area than the hierarchical NIC 400 and 450 design and supports new AmbiZ AXI protocols like AXI issue F, G, and H features. The NI 700 is a tree or vine-like structure that can support many-to-many masters and slave endpoints of different widths and frequencies across several power and clock domains. And all this can be designed from a single canvas design tool. The NI 700 comes with a new configuration tool that is launched from within Socrates Creator. It supports both manual design as well as automated topology creation. In this example, the blue regions represent logical blocks and the red and green squares are the AXI master and slave endpoints. The tool can derive this topology based on just a user input table describing source and destination pairs, with information on power and clock domains, average and peak bandwidth, latency sensitivity, QoS, and physical design. The automation can take that table and those blocks, keep out areas, and create an optimized topology for the NI 700 network. The tool also includes an embedded performance model to generate traffic into the mesh to, say, ideal slave nodes that you can parameterize and verify the expectation and expected behavior. After that auto route or auto synthesis tool, the user can still go in and hand tune topology to meet the desired behavior. So you can start with either manual, ad hoc. You don't have to know the placement of the devices at first in order to design this. You can just start developing by hand to get used to it. Now that I've described both the CMN 700 and 700 interconnects, I'll show you an example of how these might work together in a combined interconnect solution. So here we have CMN 700 in gray in the center, and over on the right-hand side, a couple of PCI endpoints or root complexes that are connected to the NCI. You can have more devices like NICs and storage and other things, other small USB and so forth. But for the example, I'll just show you somehow the transactions and animation. For a typical CPU transaction, it would go from the CPU into the mesh and go through first to the system cache and snoop filter to check if there's any known cache there. If it misses both of those, then it is forwarded on to the slave node for memory. Say if the transaction then that instruction was to ascend a peek or a poke to the PCI Express root complex. It would then go across the mesh, bypassing the system cache, and go to an HNI or an HNP node to talk to the device and poke and peek something. That may have kicked off a transaction to go fetch memory from someplace, and would go through, say, the system MMU for address translation, for IO virtualization or protection. Maybe they would go down to maybe poke or look at an IO slave node for some other extra information. And then it can even do peer-to-peer communication through the SMMU to do address protection and IO virtualization. Or it can go directly, say, for vendor-defined messaging. You can go directly from bridge PCI through the NI700. I'm going to transition, talk about interconnect, from interconnect products to ecosystem and design and development tools to help your architects design and validate the interconnect for your SOT design. We know that developing an SoC can be a daunting task, and it always helps to start from looking at some examples. As part of our own internal validation process, we integrate our own CPUs, interconnect, and system IP, and even third-party IP into representative systems we call reference designs. From this experience, we've created the equivalent of a recipe that will show you how to make something similar. This has been very helpful for our partners' architectural phase of development. With these reference designs, our customers are able to estimate how many CPUs, cache, memory, and mesh topology they need to achieve a certain power, performance, and area objectives. These reference designs have helped our partners get to market faster and reduce their risk because they are starting with a known good recipe. Best thing about this is the material is all free for our partners. Now, we don't give away the RTL. Instead, we provide enough documentation, benchmark performance results, software accurate fast models, software drivers, and firmware source code for boot up and configuration to give you confidence that you can build something similar and obtain similar results. Just go to the link below and you'll find out more on this page. Here is a range of some of the reference designs we've done in the past and we're currently working on, and some of what we plan in the future. The RDN1 hyperscale in the top center is very close to the architecture in the AWS Graviton 2, for example. And we just finished up a 16 and 32 core V1 reference design in the lower, and we're just now starting to produce results for a 32 core N2 reference design that includes the CMN 700 and NI 700 designs. And we have plans for even more in the future. So once you've passed the architectural phase and narrowed down what you want to build, and you want to dive deeper into the interconnect topology and component placement, you'll be using our Socrates IP creation tool to configure the mesh. The CMM IP is delivered as actual component RTL pieces that Socrates assembles into the final RTL. Socrates ensures that the finished CML RTL is error-free, allowing you to connect to CPUs, memory, and I/O components with confidence. It also includes CCIX and CXL gateways to ensure compliance to AmbiZ standards interfaces from CHI, AXI, ACE-Lite, and CXS. I would also like to take this opportunity to introduce a new RTL debug tool for AmbiZ interfaces and interconnects that we're developing called AmbiZ. And that will be available early next year. With the AmbiZ desktop application tool, you'll be able to extract information from standard waveform files like VCD, which then the tool correlates with the interconnect config and AmbiZ protocols to generate meaningful graphics and tables. This tool helps you visualize transactions, say on a ladder diagram, or congested areas with heat maps, or even link request to response transactions, or even spawn transactions that would otherwise be too hard to follow in a general waveform. For more information on this, you can ask your ARM sales or FAEs for a demo, and they'll also love to hear your feedback on the tool. In summary, designing an SoC with interconnect IP is more than just RTL. You'll also need system reference designs and with power, performance, and area data to show you like a how-to guidance. You'll want performance models for sizing and optimizing component placement on the mesh, and some user-friendly GUI like Socrates and scripts to quickly configure and build error-free RTL, and an ecosystem of development and test and debug tools like the upcoming AmbiZ. Well, thank you. That's it for my presentation, and I welcome your feedback in the chat session, and hopefully I'm answering it as we've been talking. Thank you.